All right, welcome back to another episode of Scientifically Simple. My name is Brandon. I'm joined today by Mohammed Fowd, and really interesting topic. We're going to be talking about steam boilers. So, for those of you who don't know, steam is pretty critical for most chemical plants. It's used to heat solutions, but in other instances, it's actually used to generate the electricity that we use every day, right? Turn on the lights, dishwasher, stuff like that. Mr. Fowd, take it away.
Oh, thanks, Brandon. And again, you keep forgetting to call me Mo. But
No,
yeah,
I
fine.
like to keep you on your toes.
I will let it go for sure. So we're just like doing a continuation for what we have spoke about before in our last clip about like the evolution of chemistry. And this time we're going to talk about like thermodynamics applications in chemistry, specifically the industrial steam boilers and how that applies to it. So we spoke previously about like how state function is path independent while the path function is path dependent. How enthalpy, internal energy, and entropy are state functions. Pressure, temperature, and volume are interrelated, and whenever you specify two of them, the third will be fixed. Calorimetry and heat of reaction deduction, and how the specific heat at constant pressure will always be bigger than specific heat at constant volume. And last but not least, how thermodynamics integration of chemistry led to the revolution in chemical industry. So starting with the chemical law, for first law of thermodynamics and energy balance, we wanted to talk about how we get to be calculating the adiabatic flame temperature. From the energy balance, this is the equation for the first law of thermodynamics, and on the left hand, that's basically the rate of change of internal energy, and on the right hand, this is the sum of all the heats coming in or out of the system, sum of all the shaft works coming in or out of the system, and the summation of the enthalpy, kinetic energy, and potential energy going into the system, and the enthalpy, kinetic energy, and potential energy leaving the system. So if we be neglecting the kinetics and potential terms, the rate of change of energy with time is going to basically, you're going to take all these terms out and becomes like, you have the rate of change of internal energy versus the Q, W, and the enthalpies. For a steady state system, the rate of change of internal energy with time, anything as a function of time will be going out. So pretty much in a steady state system, it will go down to the sum of Q's, sum of the work, and the enthalpies. Now for an adiabatic system that has no work performed on or by, then pretty much Q are zero, the work is zero, and pretty much it goes down to the sum of enthalpy coming into the system will be equal to the sum of enthalpy coming out of the system. And from this basic equation, we can be able to get the adiabatic flame temperature, because as we know, enthalpy is a state function, so it's function of pressure and temperature. So it's going to be initial pressure and temperature on this side, and there's going to be final pressure and temperature on this side. The final temperature here is going to be implicitly calculated from this equation. So as we have stated earlier, this is the adiabatic flame temperature equation, and basically here is whenever we have a combustion reaction, we have an initial state which is a given temperature and pressure. We have methane, nitrogen, oxygen, argon, carbon dioxide, and water. And then we want to be moving to the final state, and that final state is going to be at T that we want to calculate, but that state is going to be having different components. The methane is going to be burned, and basically you're going to end up like having only nitrogen from the air, steam from combustion, carbon dioxide from combustion, and along with the one coming with the air, argon, and oxygen. The oxygen here is going to be representing the excess oxygen. It can be zero or it can be more than zero. So, as we have stated like in last clip, that the combustion chemical reaction that we test and basically experiment in a calorimetry that takes place at standard conditions. So here is a problem. How I can get the enthalpy to match, because like whenever I'm comparing enthalpies together, they're gonna have to be at the same conditions. Like I can't compare enthalpy at like 500 Kelvin with added to another enthalpy at 0 Kelvin. So that's the beauty of the fact that enthalpy is a state function, not a path function, which means if we go back here, I technically don't need to be going from this point to this point. I can do this and go this way, or I can go down here to this point here and go up. As long as my starting point and the end point are the same, any pathway I take is going to be fine. So that's a very critical thing. When I combine it with the heat of reaction here, then I can come up with a very cool concept. What is that cool concept? This is what we have stated previously. I want to be going from P1 and T1 to P2, T2 to get my adiabatic flame temperature at T2, and we already know from the energy balance those two are equal to 0. So if I go take that pathway instead of going to this pathway and take it from the initial level or initial state to the standard state for the same feed, and then make the chemical reaction take place at the standard conditions, which we already know. We already experimentally know all of them as standard conditions. I can go to the final state at the standard case, at the standard state, which will basically transform methane into the combustion product. And then I can just go from standard state all the way to the final state. And now you can understand how the standard chemical reaction or enthalpy of formation and the equation of states are insanely critical when they are combined together. And when I look at like those pathways, I can basically split them in order to get like from here to here through that pathway. It's going to be, you take H2 minus H node, and then H node minus HI, which is basically the heat of reaction. That's the enthalpy of reaction, which we have here, multiplied by number of moles of methane. And then go from here to here, I basically go the reverse. I have this minus that. When you get all these together, you will find out it will directly go down to that form again. If you take this, if you break down this equation, you're gonna find out that this one is going to get out to this one, and eventually you're gonna basically the same. Why I would take this, not that one, is because this is experimentally provided at standard state. So there is nothing experimentally goes from here to here. And that's, by the way, every single software on the planet for simulation, how it does it. It uses the equation of state to be going from TP to T node to P node. It gets the heat of reaction at the standard conditions, and then it moves from the P node, T node to P2, T2.
So to Mo's point, that dotted line is the path that the reaction is going to take. Unfortunately for us, we don't have, most times, sufficient information to determine what happens along that path, so we create our own, right? So each line that you're seeing that's solid between the dots is a different step, either heating or cooling or reacting, and we essentially sum up the results of each of those steps to determine what that dotted path actually is going to be.
Yep.
And to Mohammed's point, we do that because we know values for each of these steps. We know the enthalpy change for heating or cooling. We know the enthalpy change for heat of reaction. We know all these things, so we don't have to bother ourselves trying to figure out what happens along the dotted line, because we can just take the solid line, and it takes, honestly, you've done it, I've done it, about 30 seconds, you got your answer. You don't really have to overthink it.
Yep. And that's pretty much what it is, because like as we have stated in previous clips in first law of thermodynamics and the equation of state, we know how to get from here to here, and we know we have to get from here to here.
Right.
If you know the equation of state and you already know the pressures and temperatures, you can calculate the enthalpy. What was added is the chemistry part. As we go to the chemical thermodynamics, it's basically chemical reactions, and chemical reactions unfortunately gets done as standard state. I wouldn't be able to be like every time I want to be like doing a chemical reaction, experimentally deduce it. Perfect. So now, moving to the cool part of thermodynamics and combustion reactions based on what we have stated so far. So going to the industrial boiler. So here we have like a picture of, of if I basically cut through a package boiler, I would look at, this is pretty much the furnace of the boiler. You have here the combustion air coming through this line. This is the combustion air, okay? The natural gas would be coming through these lines inside, and it's going to be meeting the combustion air in this flame, in that burner, and they're gonna ignite. And as they ignite, they are going to go from the radiation zone into the convection zone and out to the combustion air preheater and pretty much into the stack. So in that boiler, there are two pathways. There is the water pathway and there is the fuel flow gases pathway.
Right.
Now, the water itself, the water would be like coming through, it's gonna be preheated in something called calorifier. That's basically what the calorifier is. It meets the hot flue gases, the basically spent flue gases before it goes to the vent stack. Gets preheated. Sometimes you call it the economizer. And it flows into these sections. So here is still water. It's going to go preheated. It's going to go to saturation. And from saturation, it goes to the steam drum. That's where the steam drum, that's going to be like, transformation of liquid water into steam. What will happen is water will go down in something called downcomers. And because of the heat, it will basically vaporize and it will go up into something called risers. Those red things there, those are risers. You see them? So the risers, that's a saturated steam. The saturated steam is going to be meeting the hot flue gases in the superheaters that you have here, and it will go through 3 different stages of superheat. This is the first superheat, second superheat, and the third superheat. And from there, it's going to the steam header. So pretty much why the radiation zone is exposed to the steam drum, because the majority of energy required to vaporize or basically superheat the steam is the latent heat. That's why you have the magnitude of energy coming from radiation meeting the saturation. Then beyond that, it's sensible heat, and you can use the residual heat coming after downstream of the radiation zone of the flue gases to further superheat the steam before it goes to the steam header. Do you have any questions, Brandon, if I missed anything?
Yeah, can you start over? I wasn't paying attention.
That's fine.
I'm just kidding.
No,
you did a really good job.
No,
That was very. I like the fact that it's like cut down the middle and you kind of see the internals.
Yeah.
Really well done.
So pretty much from industrial steam boiler perspective, we have the fuel side, the natural gas, and the combustion air. So combustion air goes through this feeder blower, and the natural gas comes from a let-down station that basically have a pressure let-down station and basically have a flow meter that controls how much fuel goes into the boiler. And whenever the air and the natural gas go to meet the burner, that's how the burner looks like. If you ever get the chance to be by any sort of steam boiler, there is a glass kind of like spots where you can actually look at the burner from inside, and that's how actually operators would know if the burner is on, because if it's not, that's going to be a big trouble. If you have gas and there's no ignition, that's going to be a problem because that's the explosive enclosure. So anyway, on the water side, as I've explained on the picture, the water goes through a preheating, goes through saturation, goes to the steam drum to turn from liquid into steam, and from steam it goes to superheated case into the steam users, or basically steam headers, where it meets the distribution. That's just like in a nutshell how how industrial boiler operates, how it works in real life.
And I like this example because like like this technology is everywhere. Like every plant that
Yeah,
I've ever been
absolutely.
at had a steam generating facility of some kind. Your power generation majority, no, actually, well, I know with renewables, but 99% of it is going to be based on steam generation, right? So this is technology that is everywhere in the world.
Absolutely. Yeah, there is no chemical plant or a utility plant
Right,
that doesn't
right,
have that.
right.
Yep. So moving now to the combustion fundamentals. So as we stated earlier, the adiabatic flame temperature or fuel calorific value. You want as much as you can. You want your fuel calorific value to be as high as you can. Why? Because the higher the calorific value, the less fuel that you will be consuming. So the fuel calorific value, as many people knows, is going to be like improved if you preheat the combustion air or if you preheat the fuel temperature. But like, what is the magnitude of each? That's how the 3D model would be like showing you. It would show how critical the combustion air versus the fuel air, and you would find out that the combustion air has way more critical role than the fuel gas. And the reason why is like, when you look at the air versus fuel, mass ratio wise, the combustion air is super significant by mass. So yeah, it
Right.
makes perfect sense to preheat the combustion air versus the fuel. Because at the end of the day, if you only preheat the fuel and it's a small amount and it gets
Right,
preheat
yeah, right.
mixed with, So this is like the ABC of like, anybody like looking at improving any type of fuel system, you'll be like, okay, let's preheat the combustion air. But like another critical factor that we are going to look at is the excess air and the relative humidity of the air. Those are super critical, and they tend to be like not that much talk about them in literature. And from there, we're gonna be like defining a metric. You can see on the ambient air temperature axis over here, and you have the relative humidity axis over here, and basically shows you from those two, you can estimate how much moisture per dry air molar ratio. It basically tells you how much water to air, dry air molar ratio. And as you can see, as the ambient air temperature goes high and the relative humidity as well goes high, there is a significant amount of water in your combustion air, and it's exponential jump, as you can see. So when I take that metric and translate it into something else, which is basically, here is my air temperature again, and look at like how the flue gases oxygen would look like. Basically, I have excess air. This is basically how much mass, or basically it lump sum the air to gas ratio. The flue gases on that side here, it represents implicitly what is the air to gas ratio. So here is the air gas ratio, and here is the ambient air temperature. Along with those two, it will be showing you the moisture molar rate with incoming air. This just shows you the percentages. So when I took those two concepts now and combine, when I have excess air in an environment that has excess humidity, you can now look at how the adiabatic flame temperature would look like. Here is your excess air. The more I put air in, pretty much, and if we end up like having an air like, for example, in Louisiana, very humid, now you can see how that basically depresses the adiabatic flame temperature. When the adiabatic flame temperature goes down, it means I need to spend more gas in order to get the same heat duty. That's what it means, because at the end of the day, Q is a function of dt. So if one of the t's goes down, that means you need to basically pump the mass up to basically compensate for that, because at the end of the day, it's mass and enthalpy change. Enthalpy change goes down, mass has to go up. So when we take that and we look at it from calorific value perspective, you can see down here how here is the caloric value, here is the oxygen or excess air, and here is the air humidity, the air relative humidity. And you can see as the the relative humidity goes up, and of course excess air goes up, you pretty much the fuel almost be zero. Like you're gonna reach a point here, if you go beyond 10% excess air or excess oxygen, sorry, that's pretty much like, the fuel is like pretty much like non-existent, because like approaching zero. You want it to be as negative as possible. That's because that's how it's an exothermic reaction. So any questions about here?
All I was gonna say is for me, right? So if you're watching this,
but like by the way, this chart up here, instead of air relative humidity, you are seeing the moisture per dry air. So I'm just like, it's the same thing. It's the fuel, it's calorific value, excess oxygen. But the difference is operators would see air relative humidity, but if you are trying to model it from engineering perspective, this is what you see, and it's just see how terrible it is. Yeah.
That's what I was gonna say. So this is not like just some made up graphs to kind of prove a point. This is real data taken for a base case. So my hope and Muhammad's hope is that you'll see this information and hopefully it'll maybe make a question like, how do you prepare these graphs? How do you interpret them? How do you, I don't know, predict new information based on this information, right? So please take the time, take a look at them. Hopefully it brings up a question. And if you got those questions, you can always send them our way.
Thanks, Brandon. And now, last but not least, we're gonna go to our summary. And we have stated in our clip today how steam boilers works in real life, how adiabatic flame temperature is calculated, how the fuel calorific value, as was stated, depends on air to gas ratio, which we lump sum that into excess oxygen percent in flue gases, air temperature, gas temperature, and air relative humidity. And with that being said, I hope the clip today has been very informative to you. If you have any questions or you're requesting any kind of explanation or more details, please feel free to be reaching us on YouTube or on LinkedIn. And the floor is all yours, Brandon. Thank you.
Yeah, so I'm going to hop off on that. We just want to say thank you again for watching or listening, however you enjoyed. This is a passion project for Mo and myself, so we really do spend a lot of time. I know Mo spent about 7 days in a dark closet preparing this material. We are very passionate about it, we really believe in it, and we really do want to help bring this material to others like you. So hopefully you enjoyed it. If you did, please let us know. Send us an email to sciencemadesimple@outlook.com or leave a comment, leave a review, however you might reach us, right? If you're watching on YouTube, like and subscribe. If you're listening on a podcast, subscribe. Leave a little comment in the reviews below. Really got a whole lot else. That's all I got. Sign it off.